Hi there, in this video we are going to be going through one of the aspects of calculus applications here. So the syllabus here mentions kind of four different things: related rates problems, rectilinear motion, optimization, and marginal cost. So there's really four things there. This video here we're going to be looking at the idea of marginal cost. Okay, so first of all, some basic definitions from economics: cost, revenue, and profit. Pretty simple terms. Cost to produce X items, revenue from selling X items, and the profit is the difference between your revenue and your cost. Okay, so this is very applicable business kind of stuff that we're going to be looking at. So we want to know what the marginal cost, marginal revenue, marginal profit is. So the derivative, if we say that C of X is the cost, then dC dx, the derivative for a small value of X, for a small change in X, so if delta X is equal to 1, then dC dx, the derivative, is just the change in the cost. So the derivative here is the approximate change in the cost when the number of items here changes by 1. It's called the marginal cost. So if we've got a cost function, the derivative with respect to X is called the marginal cost. Similarly, the derivative with respect to X of the revenue, where X is the number of items that you are selling in this case, is called the marginal revenue, and dP dx is called the marginal profit. Okay, so it's important to understand that this derivative is not giving you the average cost per unit at that stage. We can get that by saying, after we've produced 1,000 units, how much does it cost us divided by the number of units? That gives us the average cost. But this function here, the marginal cost function, gives the approximate cost of producing one more unit at the stage of production that has just seen the xth unit produced. So C-100 will be the approximate cost of producing the 101st unit. Okay, it's called the marginal cost. All right, so there's the definitions there, and of course the marginal revenue. So MR, or just R-X, the derivative of R with respect to X. Okay, so let's look at a graphical kind of way of looking at this. Here's a graph where we've got a cost function and a revenue function. So the cost function is pretty simple to understand. And by the way, these axes, this is X along the bottom here, which is number of items, and this is just money along the top here on the vertical axis. So we've got a fixed cost for startup, so that's our buying our machinery, etc. So this is X equals 0, so we haven't actually produced anything, but it still cost us something to get started in this procedure. And then you can see it's going up in a linear fashion. That means as we produce each item, the cost goes up by a fixed amount. Okay, so it's costing us say 30 cents to produce each time. So the gradient of this line here would be 0.3 in that case, if this is dollars along this axis here. The revenue function is a little bit more interesting. You can see we start down here at 0 with 0 revenue, which of course we're going to have 0 revenue if we're selling 0 items. And you can see the revenue function goes up, it's increasing, and then it starts to go down after a certain amount of time. So after we start producing a lot of items, the revenue starts going down. Okay, so let's try and figure out what's going on at certain places on this graph here. So if we look at this point here, you can see the slope of the cost function at that time. That is going to be, the slope of the revenue function. So here we're going to be talking about the marginal revenue, okay, the slope. So the slope at that point, you can see, is steeper than the slope of the cost function. So what does that mean? That means that we're making more money as we go along here. The amount of money, the marginal revenue, is more than the cost. So we want to keep producing items at this stage, don't we? Because our revenue is increasing at a greater rate than the cost is at this time. And of course what we're interested in is finding the place along here where we're going to make a maximum profit. That's what we're interested in. So if we chose another place along this curve here, further along the green curve, we would see that the slope of the revenue function is actually less than the slope of the cost function. So that also isn't going to be the best place, because our revenue is going down, our marginal revenue is going down, whereas our cost of making something is more at that stage. Okay, so the marginal cost is more. So we're looking for the sweet spot here where the profit is going to be maximized, and I think most of you could see where that's going to be. It's actually right here where the slope of the revenue function is the same as the slope of the cost function. Okay, that's where we're going to get our maximum profit, because profit's just revenue minus cost. So the maximum profit's going to happen when the slope of the cost function is equal to the slope of the revenue function. That's where that distance between those two curves actually is going to be the greatest as well. Okay, so that's what we're looking for. So you could say that the profit, we're going to want to know when the maximum profit is, and of course we know that maximums happens when the slope of this function here, the profit function, is equal to 0. So in other words, we want to know when the derivative of the revenue function minus the derivative of the cost function is equal to 0. That's going to give us our maximum profit. So there's some calculus going on with this situation here. Let's look at some examples. So we've got some real equations here. We've got a cost function, 6x plus 10 root x plus 500. This looks like this is our setup costs, and we've got a mathematician to model what our costs are depending on how many items we produce. So this cost function here is a little bit more intricate than just a straight line. So let's answer these questions. How much does it cost to produce 100 items? So if we substitute 100 into there, that equation there, we get 1,200. So it costs us $1,200 to produce 100 items. Find the average production cost per item when x equals 100. Well, that's easy. We've produced 100 items. It's cost us $1,200. That's an average of $12 per item. Find the expression for the marginal cost. Okay, so this is the derivative now. So you can either get your calculator out or do the derivative, and you'll find that the marginal cost is 6 plus 5 over root x. Okay, that's the marginal cost. So use our answer to C to determine the approximate cost of producing one more item at the stage in the production where x equals 100. That is just C-100. Okay, that's the cost of producing the 101st item. So we substitute 100 into our marginal cost formula here, and we get 6.5 or $6.50. Okay, that's what we call the marginal cost. And again, this thing is constantly changing as we go along here. Whereas in the last example I just showed you, the cost was just going up in a linear fashion. This one here, a little bit different. This marginal cost is going to be changing all the time. So whereas that last example, it was pretty simple to see the maximum profit. In this case here, if we had a complicated revenue function, the calculus is really going to help us out. Okay, so it's going to cost us approximately $6.50. So you can see, without even drawing this, I can see that overall the average has been $12 per item, but now once we've got to the 100th item, it's only costing us $6.50 to produce the next item, and I anticipate that that would keep going down. So the more items we produce, the marginal cost is going to keep going down. Okay, last question says compare our answer for D for C101 minus C100. So if we just work out the cost of producing 101 items, subtract off the cost of producing 100 items, we'd put all this on our calculator, we get very close to $6.50, so you can see those two are the same. Okay, this question. Once again, this cost function is much more complicated than just a linear function. So here's our cost function. We've got that the items sell for $1,850 each, so I think big screen TV. Write expressions for the revenue function, the profit function. Okay, so what's our revenue going to be? So our revenue function is just a real simple one. This one's linear, 1850x. So each one of our units is just going to sell for 1850. So our profit function is just revenue minus cost. So 1850x minus all of this thing up here. Okay, so when we do that, we get this function here. Now if we wanted to maximize the profit, we'd just do the derivative of this and set it equal to 0, and that would give us a maximum profit. So the second part of the question says evaluate C-160, R-160 and P-160 and explain what your information your answers give. So we do the derivative of the cost function, that is this thing here, and we substitute in 160 and we get $1,080. The marginal revenue, the derivative of this function here, which is easy, 1850, so it doesn't matter where we are or how many units we've sold, the marginal revenue is always 1850. And the marginal profit, so that's the derivative of this thing here, and then we've substituted in 160, we've got $770 per unit. Now, what does each of these things tell us? When we've produced 160 units, it will cost us about $1,080 to produce the next unit, but we're getting in $1,850 per unit there. So it's good to keep going with the number of units that we're producing, okay, because our revenue is exceeding our cost. You can see our profit at that time is $770 per unit. So we want to keep going, right? We want to keep going until these two things are the same. When our revenue and our cost, the marginal revenue and the marginal cost are the same, that's going to be the sweet spot where we're going to make the most money. Okay, in this question here, we've got the marginal revenue. So we're given the marginal revenue and we want to get the revenue function. So this is an integration question, isn't it? And determine the extra revenue resulting from the sale of 160 items rather than 100. Okay, so we do need to do integration, starting with the derivative, integrate both sides, and we end up with this. So this is the revenue function. We know that when x equals 0, r is equal to 0. Okay, when we're selling no units, our revenue is going to be 0. So that tells us that c is equal to 0. So here's our revenue function. Okay, so the revenue function after selling 100 units, 5,250. After selling 160 units is 8,640. So the difference between those two is what they asked for. The extra revenue for selling 160 items rather than 100 is 3,390. Now this is another application of definite integration here. So we could just say that the total, the difference between the revenue is just the integral here of our marginal revenue function between 160 and 100. Okay, so think of it as the area under this curve between 160 and 100. Alright, if you do that, you can see you also get 3,390.